Welcome to another episode of My Bits of Old Computer Junk. These two brutes are power supply modules from an IBM 3031 mainframe, which was introduced in about 1978, so these things are around about 40 years old. The top one there is 25 kilograms and this one is 30 kilograms, and the difference is explained by, you see all these magnetics on this one are much heavier than those. Now these things have been stored in a shed where they've had a fair bit of exposure to the elements, hence all the rust and dust and grass and spider webs and rubbish in there. So I'll clean that, vacuum all that out, and we can have a closer look at them. But first we should just have a quick look at the machine they came from. Here we have the basic system without any peripheral devices, just the core processor. In the foreground we have the operator's console. The T-shaped arrangement at the back is the actual processor. It's about the size of 5 large single-door fridges, and that's where these power supply modules came from. It was introduced in 1978, withdrawn in 1985, and by modern standards, of course, it's quite piss weak for the size of the thing and the amount of power it drew. It only had 6 megabytes of main memory and cycle time of 115 nanoseconds, which is like, 8.5 megahertz, so yeah, wow. But the important thing here is, when looking at these power supply modules, is the other unit, the 3017 power unit, which is about the size of a couple of washing machines. And here's its specifications, and there's very little information on this thing. Elsewhere I did find this. I knew it was a motor generator, but I didn't know what it output. So yeah, it's basically a motor and a generator. It provides 208 volts at 415 hertz. Now the advantage of doing things this way is that the processor unit has a consistent input of 208 volts, whether the mains is actually 240 or 120, 3-phase of course. So you just put in a different motor. The generator is still the same. Another advantage is that all that rotating mass in the motor generator gives it some protection against power surges and power brownouts. And importantly for the design of the modules that we're looking at, the 415 hertz, much higher frequency than 50 or 60 hertz, enables reduced size of magnetics and capacitors. So let's have a look at the module itself, cleaned up a bit. Well, there they are. I've brushed them and vacuumed, so a lot of the crap's gone. I suppose I could have tried to hose them down, but these things have suffered enough moisture exposure. Back in the 1980s I scrapped 1 or 2 3031s, and these come from that. I believe there was at least 4 of these things in a 3031, maybe even 6. These are the only 2 that I've got that are more or less intact. I have kept parts from the others. I might show you some of those later, but let's just look at what stands out on these things. Earlier we saw that there's this 3-phase transformer with very high current leads. This at the end here is an inductor, and on the other side we've got 6 electrically isolated heat sinks, insulated spaces there, and each of these contains a fairly hefty silicon control rectifier, SCR. I can't find the part number on that. It's some special part number for IBM. It doesn't show up in any data books, so I'm not sure of the specs of it. But I'm guessing of the order of over 100 amps. And obviously these output terminals indicate large numbers of amps coming out of this thing. This is a shunt to measure the output current, and the sense wires there go to the control electronics. And this is one of the control boards. It's only, I don't know which one it came out of, but according to these labels, there's 2 or 3 circuit boards go in there into these sockets over here. See, there's control and protection. I don't know which this is, or if it even came out of that one. And then 2 connectors going off to somewhere else. So they're basically the same construction, but there are differences. For instance, this one's got a largish electrolytic capacitor, which is, for a power supply, there's not many electrolytic capacitors in here, and only pretty smallish ones. and then there's a couple of, and this one doesn't have that electrode. And there's also a couple of high power resistors there, which this one doesn't have. The terminal block here has got 8 pins on this one, on the other it's only got 4. And it looks like 2 of them are for incoming power. And on the 4 terminals on this one, it's not clear which ones might be the input. Turn this one over. There's the 4 terminals there, so okay, one of them's free, but which one of those would be the incoming power? I'm not sure. There's also a little 3-phase transformer down here with lots of fine wires that go around to the control electronics. So I'm not sure what he's about either. And if we turn it over again, this one has 3 circuit boards, but here's the interesting bit. 2.3 volts at 250 amps. This is a brute. And down here we have another heat sink which has 5 rusty TO3 power transistors on it. This one has 2 lots of 5 power transistors on it, so I'm not sure why that is 2 lots and this only has 1 lot. So what I want to try and do is reverse engineer it a little bit, just try and get the basic architecture of it, topology, see what's connected to what, and see if we can find anything interesting in that. Oh yeah, this one, 250 amps, is the one with the smaller magnetics, so maybe this brute does even more amps. There's no labels on that one to say what voltage or current it produces. Yeah, so I'll try and work out how this thing's wired up. So out of all this over here, there's 2 large output bus bars which go to the output terminals. Top bar goes to the top 2 here, so that's one side, and the other one goes to here, part of the shunt. So the output's taken here on the other side of the shunt, so I can measure the current going out. So there's one terminal, those 2, and there's the other terminal there. The bus bar goes to these ones. Now, there was also, these studs here did go to these 2 rods, which were so rusted in they snapped off when I tried to unscrew them, and they secured onto there. These 2 strips, copper strips here, went onto those. So what's going on here with fairly heavy current carrying conductors there and power transistors sitting across the output, and lots of diodes. This here is the output current shunt sense terminals, so something to do with that. And actually they go into the electronics, not into here. And lots of wires coming off that little 3-phase transformer on the other side, which connected to all these here. So yeah, I'm not sure what this thing's about, with its 2 straps going to the power transistors. What could that possibly be doing sitting across the output? Fine regulation, perhaps? A fine shunt regulator? Yeah, it could be, I guess. Whatever, there might be some ripple on here and or slightly higher voltage than 2.3 volts, and maybe that acts as a shunt regulator to just pull it down to exactly 2.3 volts and manage the ripple a bit. Just guessing. I'll keep pulling things apart. Right, things have become a bit more clear now. I'm not sure what I was thinking before about this terminal block. I was thinking 2-phase, single phase rather. Of course it's 3-phase, and it's fed from a Y configuration, 3 phases and neutral. See, so we get those 3 go down to the transformers, and a common neutral also goes down to the transformers. The 3 phases also go to this little 3-phase transformer, which goes to the electronics. Now this piece of electronics here, what I call the shunt board, is 2 completely separate circuits. There's the transistors and these 2 connections that go to the output bus, and there's all these diodes and capacitors down the bottom. This lot here is a giant Darlington transistor. 4 of these are in parallel with their emitters going through ballast resistors down there to that terminal. This terminal goes to the collectors, and the 5th transistor drives the other 4. So looking at the back, there's all the collectors, because bolted directly to the heatsink, there's no insulation, but this was insulated from the case, of course. So yeah, the collectors go there, and there's the bases driven from the emitter of this one, and this drives that. So that's just a big transistor sitting across the output. This here appears to be a 3-phase 4-bridge rectifier coming off of this transformer. So that provides some local power that then goes to the electronics, and there's also wiring coming off of this that go to the electronics. I suspect that's just more or less timing signals so that the electronics know when to fire the SCRs, which is done via this last wire here. Six leads go down to the SCRs, and there's 3 SCRs on each side go to this little 3-way terminal block. That's where those wires go, and then to the gates of the SCRs, same on the other side. And also to the control board goes the output current sense terminals. So we can get rid of this now, and all that's left to do now is work out the wiring on these transformers. So yeah, I can disconnect this guy and then buzz out these connections to see what goes where. Getting there. Just a note to self, the incoming phase wires are 1, 2 and 3. The little transformer had wires 1, 2 and 3 going to those 3 terminals, so he's now disconnected. But the big transformer, the wires are 1, 3, 5 and 2, 4, 6 I presume over here. I've disconnected the output bus from the output terminals, disconnected the transformer secondaries from the SCR anodes. The SCRs are stud anodes, so they go straight through to the heatsink. And I've disconnected the SCR cathodes from the other output bus. So this thing should now lift off, hopefully. And it does. A few kilos there, and some crap. So you can see the SCR gate control wires, got these terminal blocks. This also went to the cathode of one of the SCRs. None of the others have that, so that's just some reference to this terminal here, this output bus. So getting there. I should be able to work out how this thing was wired now. Earlier when I peeked down under there, and I could see that there was 3 wires going into each transformer, so I thought maybe there was a centre tap arrangement going on, but no, there's just 2 wires going in. The 3rd wire comes out to the frame from all of them, so that's just an electrostatic shield, and there's no connection between that and any of the other wires on these transformers. So now I can show you my circuits for these things. So this is what's on this board. As I mentioned, there's 2 completely separate circuits. There's all these diodes and capacitors, which I think will end up forming a 4-way 3-phase rectifier. I don't know why there's 6 of everything. A lot of wires coming off this, which goes to there. So as far as I can tell, it just seems to be a power supply for the rest of the electronics. And up here we have a big Darlington transistor. There's 4 transistors with their base resistors, which I estimate to be about 0.1 ohm, 5 watts, to equalise any differences between the four, and they're driven by the fifth transistor, which drives their bases, so that's the control signal for it. And there's 27k resistors from each emitter common together, which I presume is so that it can sense the voltage across the ballast resistors and come up with an idea what sort of current's going through it. And the rest of the unit, so we have the three transformers. Each one is connected between one of the three phase wires and a common neutral over here, as well as this little guy down here comes off the three phases. There's 22 wires go to the shunt board, to all those diodes, and 6 of them go to the electronics area, which I presume is timing signals. On the secondary side of the transformers, they're centre tapped, and there's a SCR anode going to each side winding, and the centre taps are all common together, going through the big inductor to the output terminals via the shunt resistor that senses the output current. The cathodes of all the SCRs are common together, and that forms the other bus bar. The 6 gates come out to a connector which goes to electronics, and then all these transistors, which form a great big Darlington, sit across the output, and that's driven from the control board. So my understanding of how this thing works is this thing provides a local power supply. I've got no idea why it needs so many wires and diodes to do that, but that's all I can think of. These signals tell the electronics what's happening with the incoming phases, so it knows when each of these 6 half windings are about to go into their positive half cycle, and it can then turn on the appropriate gate to connect the positive from that through the SCR to the output. And of course, to do the regulation, it may delay how far into the cycle before it fires the SCR. So for light loads, it might wait a while, maybe even not even fire the SCR at all on very light loads. And the inductor smooths out the ripple. Remember, this is all happening at 415 hertz, and we've got 6 pulses per cycle. So I think that works out to like 2400 hertz ripples, which is a whole lot better than 100 coming out of a single phase. So that big inductor will help reduce some of the ripple. And all I can think that this big Darlington transistor arrangement does is acts as a shunt across there, so that all this produces slightly more voltage than what you really want out here, the 2.3 volts, and the shunt regulator simply pulls it down to 2.3. That's what I think anyway. Could be wrong. Let me know if you think there's a better explanation. So there you have it. Big old power supply, 1978. Hope you found that interesting. I don't understand three-phase transformers very well. I've always been a bit puzzled about how they can share a common core and not interfere how the phases can't interfere with each other. So what I might do is stick some volts into one of these and see what comes out all the other windings, just to try and get a better understanding of how these things work. But if anything interesting comes of that, I'll make another video. But I almost forgot. I was going to look at the differences between that slightly smaller unit and this slightly bigger one. Obviously, same operating principle going on, but there are some interesting differences. This one, as well as having bigger transformers and inductor and heavier wires, so we'll call this one, say, 350 amps. Instead of 4 terminals, there's 8 here. Still got the 3 incoming phases going to one side of each secondary, but the other sides, instead of being common together at the neutral, are brought out next to each of these phases. So we've got 1, 2, 3, but there's also these extra 2 with a little loop running between them. It'd be interesting to find out what that does, but I don't really want to pull this thing apart just at the minute, so that will have to remain a little mystery. And as I mentioned before, this one has these 2 power resistors and a mid-size electrolytic, which the other doesn't have. But also there's a few more connections, not just to the gates with these little wires, but there's a few other things. For each secondary half going to each SCR anode, there's a wire and there's also another wire connected to the common centre tap of the transformers before it goes into the inductor. So I'm thinking these provide the timing information that the other one inferred. If we look at the circuit boards, this one has a control and protection board, whereas the other had control, protection and timing. So maybe these connections to the SCR anodes or the secondary outputs do the timing that the other one was having to infer from what it saw coming out of that little three-phase transformer on the other side. Just a guess. And the other difference is these, it's not 2 lots of 5 power transistors, there's actually 6 on the bottom one. So what we've got here is 10 transistors in parallel with one driving them, and that's borne out by there's 10 ballast resistors down there. So that's an even bigger Darlington transistor sitting across the output, which makes sense. More current, you need more shunting. And I think that covers everything different about this one. Yeah, so I don't want to pull that one apart just yet. And the other one used cable ties to join the loom together, so it was easy to unravel. This one has got actual string loom, and I don't really want to pull that apart. So that covers this one. Oh, and I'll show you a few of the parts of it. There's an inductor from one of these. It's the same size as that, and he weighs 6 kilos. And there's the current output shunt from one of the others. So this, the bus bar that all the SCR cathodes go to joins to that. There's the resistance elements, and there's the output, and between these 2 screw holes you've got the current sense. And you've already seen the SCRs, which are General Electric, I believe, here, GE, but with a funny bugger part number. So there we have it. For now, that's it for these things. I hope you enjoyed, and please give it a like and subscribe if you want to see more of this sort of junk, and I'll catch you later.